Okay. So basically, as Professor Dimitri said, I'm basically looking at the two-dimension modeling of reductive nitrosylation. Okay, so before I dive deep into the math and everything, first of all, I would like to introduce to you guys what is heme. Basically, it's a large class of metalloproteinate that plays a vital role in biological processes such as electron transport, oxygen carrier, and other reactions. So basically, a Pothorn ring consists of four chiral rings that are bound. Sorry, that are linked to each other with the a methane group, and usually the iron atom that is usually iron 2 or iron 3 is at the center of the porphyrin ring by the interactions of the nitrogen. And basically, many heme proteins are known to interact with nitric oxide, resulting in a number of reported ligation and oxidations for their respective complexes. So, um, ferric heme nitrosylase complexes are generally thermodynamically unstable, so they form the ferrous heme nitrosylase. And basically, the mechanism that happens is a nucleophilic attack upon the nitrosyl nitrogen by a hydroxide or any base. Then that follows by the dissociation of nitrous acid, leaving behind the reduced pentacoordinate ion center, which is rapidly trapped by an excess nitric oxide. And then the conjugate base of the released nitrous acid and nitrite ion then serves as uh, for, subsequent rounds of reductive nitrosylation. And basically that video, okay, yeah. So basically you guys can see the video here. The oxygen comes in and the nitrogen then is released from the iron and then binds to the oxygen. Okay. Oops. Okay. Okay. So basically, in MATLAB, I modeled the reaction of the nitrous acid formation. So in order to do that, I tabulated the values of two key interactions, two key interatomic distances, x and y direction, and the corresponding value of the total potential energy at each time step of the molecular dynamic reaction. So basically, here I have defined my potential energy as the hydroxide approaches the catalytic center and the nitric oxide group. And basically, decay is my potential width, potential depth. W is my width of potential. I basically, as I said, defined it in X and Y direction, which is what I was interested. And basically, in order to describe such movement, one uses the time-dependent Schrodinger equation, which we have learned by the evolution operator, and then after in terms of Hamiltonian operator, uh, and which is composed of the kinetic energy and the potential energies. And then here's the key part. So basically, one defines Kmax grid points for x dimension, which is I, and for the y dimension is y. And so basically, in order for one to represent the kinetic energy of this reaction, one needs to take two indices, x and that describe the x and y degrees of freedom for the wave function, and then take four indices for the unity operator. And basically, by taking the Hamiltonian operator and the unity operator, the product of those two, you get the kinetic energy. And then because MATLAB doesn't like that, we have to then translate those four indices into two super indices, which are then labeled I and J. Okay, so basically here is the kinetic energy. So basically Ki and J is the kinetic energy operator, and then one is the identity operator in respect to other indices. And then the initial wave function in two-dimensional momentum space was defined by taking the product of the initial wave function in x and y direction, and which I then basically defined the wave function. You guys know that? Okay, so then probability distribution. Okay, so then the wave function is converted into a form of probability distribution by taking the integration of that distribution in terms of values coordinate x minimum, x maximum, and then the intermediate x internal for y internal, y minimum, and y yeah. Okay, so basically here I noted that the sum of all these will be equal to 1. Then, okay, then using the snapshot, basically the snapshot of this figure, I then obtained the table, which combines the figure and summarizes the interactions, the distances, and the potential energy of the reaction. Okay, here's a potential energy surface. Here's a video that you guys should pay more attention. Oops. Okay. Oops, no. Gotta play the video. Okay, yes. Okay. So here's the video, as you can see. In the video, I'll show the real part of the wave packet, and the blue color symbolizes the negative charge. Yeah, and then the orange or the yellow is the positive. And I ignored the imaginary part of my wave packet. Okay, so oops, let's stop it here and go. So oops, yeah. So then, okay. So basically, how would I expect the reaction to work? You start at the initial position, and then over time, you start from the reactant side, and over time, we expect it to go to the product side. Okay. So after I did that, using the first order rate law, I calculated my rates, and then obtained the following plot, which is the Arrhenius plot. And like looking at my plot, we can say that we have a spontaneous reaction that goes in the downhill direction, which also corresponds to negative activation energy. So basically this means that the reactants has more free energy than the products, and also like although this is an unusual case or whatever, so the reason why this might happen is because maybe another constant, basically the equilibrium constant, is also inputted, or it's also at the same time is inputted. So that's why we see that that we have a negative activation energy. So we end on questions.
Okay, please join me in thanking Cyril. So any questions online? Please speak if you have questions. Any questions in the audience? I see question in eyes of Adam. No?
I have a question. So,
yes, please.
To my understanding, you are doing hydrogen tunneling in two-dimensional space, right?
Is it hydrogen or hydroxyl?
It's hydroxy, like hydroxyl in two-dimensional. So basically, the hydroxyl and my oops, hold on, do I have the reaction here? Oops. Okay, no, I do not. Probably do not. No. Okay, so basically, the hydroxyl and my nitric oxide will react and then form the nitrous acid. So I'm looking at the two-dimensional reaction of that mechanism.
Maybe let's watch the movie of the actual reaction.
So The beginning or the
Yeah, the beginning when you show the movie.
this
yeah,
one?
yeah, this one.
Okay. So basically, here we have our porphyrin ring, and then we see initially. Okay, so it's quite fast, but hopefully it plays again. I'll just stop it in time points. So okay, so initially our nitrogen is bound to the iron center of our porphyrin ring. So then hydroxide get introduced into the porphyrin ring, and then that hydroxide forms and bonds with that nitrogen, and forms a bond with our oxygen, whereas the nitrogen iron bond breaks. Okay, so then we have the formation of our um, our nitrous acid, which you can see here. I hope that explains your question.
Okay, so in the wave packet dynamics,
Say that
so
again.
what is your mass?
What is mine? Can you say that again?
Dr. Khan, please repeat. What is her? What?
So in the wave packet dynamics, you should have mass, right? So
Oh,
is
mass.
oxygen or something reduced mass?
Yeah, so my mass would be of oxygen. Does that answer your question?
Okay.
So I think I use the mass of oxygen. Any more questions?
Yes, I see there is a question of Adam. And if one, here is my comment to Dr. Khan, the bond between iron and nitrogen would correspond more to the mass of the whole nitrous acid. So one should use different masses for different dimensions if one wants to get really precise results.
Okay.
I got two questions. So, could this be used in like organic reactions, or could this be like a some sort of catalyst? Like you input nitrogen oxide and then you're given this nitric component. And my second question is, how did you generate the figures at MATLAB?
This one?
Yeah.
Well, it's not MATLAB, that's for sure. It's well, if you go online, there are different websites where you can like plot, like you can input what the shape of the reaction you're looking at.
Oh, that's fast because is it end of your question? Let her answer.
So if you go on, like, there are different websites where you can like they can help you like plot your reaction mechanism in a more video graphic way. So yeah, so that's how that was done, not using MATLAB, definitely. Also, your first question. Yes, you can use it for you said organic. Oh yeah, yes, you can definitely use it, but you just have to change. Yeah, you have to change some parts of the code to fit the reaction you're looking at, if that helps answer your question.
Yeah.
Okay.
Okay, yes, I think do not leave. Maybe there will be more questions. Let me.
Another question. So how did you prepare the potential energy surface, and what is your barrier height for the reaction?
If you can answer. If you cannot, I will help later.
Okay, the potential energy surface.
Maybe show the table.
Yeah, that's what I'm saying. Oops, sorry. So, so basically, I inputted this table into MATLAB, and using that, I was able to calculate the potential energy and how.
Okay, okay, yeah, thank you. No, do not leave. Maybe there will be more questions. So let me comment on this answer question of Dr. Khan and question of Adam. This is a perfect point to advertise the next elective class, computational chemistry 476. Methods from that class were used here, and one of the students who took this class in the past, I think it was Braden Waite, did this project and provided the data, and they were stored for like a couple of years and then brought up for Sibel to continue. So the method how this data were calculated is away from the scope of this class. It was borrowed from a student who took next level higher class. The question about the barrier. There is no barrier, and it is a main result that Sibel did deliver. So instead of barrier, there is a dip in between reactant and product, which can even trap the intermediate, and therefore her activation energy was negative. So it's spontaneous reaction that would happen anyway, even without thermal activation. Adam, does it answer your question? You and Dr. Han, does it answer your question?
Yes.
Okay, one more. So, Sibel, you're popular.
Apparently, I didn't want to be popular.
So if there's a dip in the potential energy surface, are we actually expecting this to happen, or are we expecting to end up with the intermediate as our final product?
Okay, Sibel, please try, and if something happens, I'll continue.
So, okay. So I would say we would expect it to still happen, right?
Yes, correct.
Okay, because
And let me add a comment. So the downhill potential is so big so that system accumulates enough kinetic energy and inertia that it passes this bound state and will still proceed to the product. If one cools it down during the reaction, it may stick into the intermediate. Does it answer your question? Okay. More questions to Sibel? So we break the trend, no questions. So what a surprise. Yeah, well, thanks, Sibel, once again. So